In this screencast, we look at the same problem that we did earlier, in which we have a disk rolling down an inclined plane with a constant slope. And instead of using the sum of the forces, the center of mass, multiplied times the acceleration of the center of mass, Euler's first law and Euler's second law, which is the time derivative of the angular momentum about the center of mass is equal to the moments about the center of mass, we'll now work this using an arbitrary point. And the arbitrary point that we've defined here is the point of contact P as it moves down the surface. So P isn't attached to the rigid body, so we can't apply that instantaneous velocity being zero. Instead, the velocity is going to be the point P as it rolls down the surface toward point O. So this means that the form of Euler's second law we'll be using is where we take the time derivative of the angular momentum about point P as observed in the inertial reference frame, and then it's the moment at P, but then we have this additional term, which is our inertial moment, and that accounts for the movement, particularly the acceleration of point P with respect to point O. So let's start by defining what we know from the last time we worked this problem. And so we first define our reference frames. We have an inertial reference frame and a body fixed reference frame, E1, E2, and E3, and B1, B2, and B3. And note here that the E3 and B3 vectors are into the page, and that means that our coordinate theta, which is clockwise, now gives us this relationship between the reference frames. Omega B as observed in I is theta dot in the B3 direction. For our kinematics, we define a position vector of g with respect to O, which is x in the E1 direction plus r in the E2 direction. We take the time differentiation 2 times and get x dot E1, x double dot E1. And then our constraint is that x dot is equal to negative r theta dot, because the center of mass is going to move in a linear fashion down the ramp in the E1 direction. And so that gives our inertial velocity and inertial acceleration of the center of mass to be negative r theta dot in the E1 direction, and then our acceleration to be negative r theta double dot in the E1 direction. And so now let's apply Euler's second law in this generalized form, where we take the time derivative of the angular momentum about an arbitrary point and set it equal to the moment about the point plus this inertial moment term. Now when working through this, you can see there's a lot of vector terms here, so take your time and work through it step by step by step. So we'll start by defining the angular momentum about point P. And that's this expression that relates the angular momentum about point P with angular momentum about the center of mass with this extra term. And so breaking this down, we have the angular momentum about the center of mass, which we know is the moment of inertia about the center of mass, omega b as observed in I, which we've defined as I sub g theta dot in the B3 direction. And then next, let's take a look at each of our vectors. We have the position vector of P with respect to g, and then the velocity vector as observed in the inertial reference frame of P with respect to g. And so we define our vector r of P with respect to g as r of P with respect to O minus r of center of mass with respect to point O. And defining each of those vectors, the position vector of point P with respect to point O is x in the E1 direction, and we've already defined g with respect to O as x in the E1 direction plus r in the E2 direction. And this corresponds with our figure. And then when we add them up, we get negative r in the E2 direction. Let's take a look at our figure, and we see that the position vector of P with respect to g should be r, the distance r, in the negative E2 direction. So the expression that we came up with makes sense. So the next term that we need is the velocity of P with respect to g in the inertial reference frame. That's the time derivative of the position vector, and so it's the time derivative in the inertial reference frame of negative r in the E2 direction. And so the time derivative of negative r in the E2 direction is equal to 0. And this is a great finding, because when we substitute all this in, we get that the angular momentum about point P is equal to I g theta dot in the B3 direction, and then we're adding our mass multiplied times negative r E2, and we're crossing it with 0. So it means that this entire term here goes to 0. And so our angular momentum about point P is equal to our angular momentum about the center of mass, and that's equal to the moment of inertia, theta dot, in the B3 direction. Now let's take a moment and make some sense of this. The angular momentum about the center of mass is equal to the angular momentum about point P, as long as point P is traveling underneath the center of mass the entire way. And this should make sense because we've got 2 points that are traveling in parallel with each other, and so if they're traveling in parallel with each other, even if they're moving, meaning that they're moving at the same velocity, then there's going to be no linear momentum with a moment arm that's creating any angular momentum about either one. And so that's why we got the expression where the angular momentums are the same with G and point P. So then to finish out the left-hand side, we have the time derivative of the angular momentum about point P. And so we're finding the time derivative of this expression, which we have a scalar multiplied times theta dot. And so this is the moment of inertia about the center of mass, theta double dot, in the B3 direction. And so here's our entire left-hand side. And now we're ready to work the right-hand side. On the right-hand side of this expression of Euler's second law, we have the moment about point P, and then we're adding the inertial moment term, which is the position vector of P with respect to G crossed with the mass of the rigid body multiplied times the acceleration of the instant, or of the point that we're concerned about, of the arbitrary point, and that's observed in the inertial reference frame. So let's start with our moment about P, which means we need a free body diagram. And so we import our free body diagram from the last time we worked this example, where we have a gravitational force that's operating through the center of mass. We have a normal force that's perpendicular to the incline, and then a friction force in the E1 direction. And so breaking down the moment about point P, it's equal to the position vector of G with respect to P crossed with mg. So there's only one force that's creating a moment about P. Point P is positioned so that the normal force and the friction force have a line of action through it, so we only need to do one cross product. And so when we calculate this, the moment about point P will be r in the E2 direction, and then it's crossed with negative mg sine alpha E1 minus mg cosine alpha in the E2 direction. And so then our final moment about point P is mgr sine alpha, and it's in the E3 direction. Next we consider the inertial moment, which is the cross product of the position vector of P with respect to G with the mass times the acceleration of point P with respect to O. And so r of P with respect to G we've already defined as negative r in the E2 direction, and to get the acceleration of point P in the inertial reference frame, we take the time derivative of our velocity of P observed in the inertial reference frame. This is the time derivative of x dot in the E1 direction, which we've used before, so that gives us x double dot in the E1 direction. So the acceleration of P with respect to O as observed in the inertial reference frame is x double dot in the E1 direction, and we've defined x double dot before as negative r theta double dot, and that'll be in the E1 direction when we apply our constraint. So now we apply these terms to our cross product. So the inertial moment is negative r in the E2 direction crossed with the mass multiplied times negative r theta double dot in the E1 direction. When we carry out the cross product, we get negative mr squared theta double dot in the E3 direction. So then the right-hand side of Euler's second law in this form is mgr sine alpha in the E3 direction minus mr squared theta double dot in the E3 direction. So now we have expressions both for the left-hand side and the right-hand side. Let's put them together. So we insert our left-hand side and our right-hand side, and we can make some substitutions. We know that for a disk, the moment of inertia about the center of mass is 1/2 mr squared. And then also, as we've defined our basis vectors in these reference frames, B3 is equal to E3. And after making those substitutions and then solving for theta double dot, we get that theta double dot is equal to 2/3 g over r sine alpha. And this is the same equation of motion that we had for the disk rolling down the inclined plane earlier when we applied both Euler's first law and Euler's second law. So I hope you see that even though this equation looks intimidating, we've got the time derivative of some point, it's equal to a moment, and now we've added this inertial moment term. And we had to do a little bit of extra work to get this angular momentum about this arbitrary point. If you choose your point wisely, then you're able to make a lot of forces cancel out, and you're able to make the math pretty easy. As we went through this, the algebra was pretty easy. You need to keep up with your terms, but you're able to get an equation of motion, which most of the time is what we're after, usually in one fell swoop, instead of having to apply constraint equations, Euler's first law, Euler's second law, and then combining a lot of things together.